Hi, my name is Calum Ferguson and I'm here to talk to you about our recent paper in RSC Applied Polymers titled Comonomer Effects in Vinyl-Based Photocatalytic Polymers. Here at the Max Planck Institute for Polymer Research, we've been looking at making the next generation of sustainable polymer photocatalysts. We do this by taking a small molecule photocatalyst, modifying it with a vinyl group and incorporating it into a range of different polymers. This allows us to increase the recyclability of the material, it allows us to increase the stability of the photocatalyst, and it also allows us to change the material properties. We do this by taking a benzothiadiazole-based photocatalyst, which is sandwiched between two phenol units, and adding on a vinyl group. That vinyl group can then be polymerized just using free radical polymerization or other controlled radical polymerization techniques. In this paper, what we've been trying to do is see what the effect the comonomer has on the photophysical properties, but also the reactivity of that small molecule photocatalyst. The polymer and the comonomer makes up the vast majority of the material. So we assumed that it would have a big impact in the outcome of catalytic reactions. What we investigated was the copolymerization of our small molecule photocatalyst with three vastly different monomers. We chose styrene, methyl methacrylate, and acrylonitrile. What we wanted to investigate was whether or not the polarity or pi-pi stacking interactions would have an impact on the photocatalyst. So we investigated the photophysical properties, so lifetime of the radical species, UV absorbance, etc. And we also looked at three different indicative photocatalytic reactions. What we found was very little difference between the styrene and methyl methacrylate based polymers, which had very similar lifetimes and absorbance. Whereas when we moved to the more polar monomer, we saw a reduction in the lifetime of the photogenerated species, and we also saw a blue shift in the absorbance of the small molecule photocatalyst. We then went on to look at some photocatalytic reactions. So we chose three pretty indicative reactions. So we chose boronic acid oxidation, we chose a CC coupling between a benzyl bromine, and then we also looked at a CC coupling between an indole and a mannanate. What we saw was not very big differences for the oxidation reactions of the boronic acid oxidation. We believe this is because it's mediated through a secondary species. It works through reactive oxygen species. Whereas when we looked at the CC couplings, we saw big differences in the photocatalytic performance. Here, the styrene-based polymers outperformed the other two. We believe this is not due to the differences in the photophysical properties, because there weren't really any. We believe this is a mass transfer-based issue, where due to the aromatic-based structure of the substrates we were investigating and the aromatic nature of styrene, we're getting an enhanced rate of diffusion to the active center, so therefore we're increasing the rate at which it reacts. We chose to publish this in RSC Applied Polymers due to the applied nature of what we were doing, where we make photocatalytic polymers and try and use them to sustainably create useful compounds, so to make high value-added compounds. Where we're going to go next with this is we're looking at incorporating multiple different functionalities into our polymers and try and understand how the material properties can be modulated and altered to affect the catalyst and increase our conversion rates. Thank you.